All right. Let's start here by looking at the syllabus right there. And if you finished this chapter 11 quiz, then you are done with quizzes. That one was due just now. And I've already mentioned that this chapter 12 quiz is going to be canceled. It's not going to happen. So there are no more reading quizzes for the class. I will remind you, you can turn in any of these quizzes late. I will take off some points, but it's much better than not turning it in at all and getting a zero, of course. So definitely feel free to turn in anything, even if it's super late. I'll take off usually 20 or 25%, depending on how late it is. And that's usually it. Okay, so the master and his emissary writing assignment is due a week from Wednesday. So you have, I guess that would be 9 days before that's due. And it will be due at the end of the day. It'll be due at like 11:59 p.m. I've been meeting with a good fair amount of people to talk about it. And I feel like it's almost always a productive conversation. So please do take a look. Um, please consider that is making an appointment to meet with me to talk about your master's emissary papers. Um, I will also mention that I've posted a new Master and His Emissary lecture video. And the lecture video will be particularly important for people that did topic number one. So there's the two topic choices. People that are doing topic number one, um, which is usually the majority of the class does that. Uh, the newest video should certainly be helpful for what I think is the more challenging aspect of topic number one. So that video was up there. I'm going to try and record a couple more of those Master and His Emissary videos this week, but I'm approaching the end of those videos. And I think honestly, I've talked about enough of things in those recordings, those lectures on Master's Emissary that you could write a good paper for sure already. But I will continue to post a few more. And I just want to emphasize, definitely feel free to send me emails so we can make appointments to talk about your paper. Any questions or comments about upcoming assignments, things things going on in the future? All right. Let's see. So we will now finish chapter 8. I think we will get this one done. There's not tons and tons left. Chapter 8, we've been talking about the motor system. I guess they call it control of action. I just think of chapter 8 as like the motor system, about movement. We've talked a lot about the brain area that is represented here, the basal ganglia, and its involvement with um, Parkinson's disease, which Parkinson's disease is characterized by reduced or too low amounts, just too low, not enough amount of dopamine in particularly the basal ganglia. So for instance, this person has Parkinson's, this would be a control. And this is a PET study, but they're, instead of measuring metabolic activity or blood flow, they're actually measuring the concentration of dopamine. At least that's what they believe is being measured here, is dopamine. Um, yeah, there's the basal ganglia. I've mentioned it's oftentimes considered subcortical, though if you look at its physical location, it's kind of above the brain stem. Um, it's oftentimes considered subcortical, but it's kind of high in the brain for subcortical brain region. So it's not 100% clear to me why it is considered subcortical, but it typically is. We talked about, where is it? Yeah. Hyper versus hypo kinesia. And these two videos do illustrate the distinction between hyperkinesia and hypokinesia. And Huntington's, by the way, corresponds to hyperkinesia. Hypokinesia is Parkinson's disease. And if you look at these kind of complicated wiring diagrams, these pathways of the basal ganglia and in other structures of the brain, like the cortex and the thalamus, these are a bunch of connections between parts. I guess you could call it a movement network in which the basal ganglia is centered. And part of the basal ganglia, I don't know if I mentioned this last time, the striatum is a part of the basal ganglia. In fact, let me show you. I think we have some. Yeah. So the whole basal ganglia is this blue part right here, and then this green part right here. And then there's some other areas that are also considered part of the basal ganglia. The striatum is like this portion of the basal ganglia, which is made out of the caudate and the putamen. You don't have to know these anatomical like hierarchies. The striatum is composed of these two subsections. You don't have to know that. But the striatum, when it's mentioned on this wiring diagram, just know that that's basically referring to a part of the basal ganglia. Same with globus pallidus. A lot of these regions inside this wiring diagram are the basal ganglia and their interactions with the cortex and some other surrounding brain regions. And some important things regarding the differences between these two conditions, Huntington's and Parkinson's. The main difference in these diagrams has to do with kind of the size of these excitatory pathways from the cortex back in to the basal ganglia, because there's kind of this loop. Stuff from the basal ganglia eventually goes to the thalamus, where it goes back to the outer cortical regions. That pathway eventually goes back into the basal ganglia. So there's a loop here. In Huntington's disease, this excitatory pathway tends to be thick, strong excitatory pathways, and kind of the result of is hyperkinesia. That is, the body and the mind are kind of constantly changing their decision about what movement to perform. And that's because of this strong excitatory signal right here. Is kind of constantly telling the basal ganglia, oh, I want to do this, I want to do this, I want to do this. I want to be constantly selecting or constantly choosing a new motor behavior. And that's happening because the signal is too strong. Hyperkinesia, the hyper part, meaning kind of too much movement. Parkinson, which is reflected in the too strong of an excitatory signal. In Parkinson's disease, which is hypo means not enough movement or too little movement. You can look at the excitatory pathways here, and they're very thin. The idea, or the way of kind of understanding this, is that excitatory signal from the cortex into the basal ganglia is too weak. And so what happens is once a motor behavior is selected, it's very difficult for a new motor behavior to become selected. So it's hard to change behaviors from one to the next. And Huntington's disease, that change is happening all the time because you're just getting a barrage of a lot of excitatory signal from the cortex. Parkinson's disease, you're not getting enough. So once you have a motor behavior picked, it's hard to override that motor behavior and to begin a new one. And so that manifests, if you watch these videos, I just checked right now, the Huntington's works. I imagine the Parkinson's video works as well. People with Huntington's disease, if you can actually watch that video, will kind of go from behavior to behavior to behavior. They'll change from one behavior to the other pretty quickly. It looks tiring when you watch these individuals because they're just constantly moving and they're changing one behavior to the other. It looks like almost like constant exercise. Compared to Parkinson's disease, they're moving a lot, but the behaviors tend to be a little bit more repetitive, which makes sense because once they select a motor behavior, they have a hard time changing it, selecting a new one, because that excitatory signal into the basal ganglia is too small. So the behaviors have more of a repetitive feel. It's not changing from one behavior to the other, to the other, to the other that fast with Parkinson's disease. It's more like once you have one behavior, it's hard to begin a new motor behavior. So this is hypokinesia. Set shifting I talked about last time, and it's also in the book, I believe. And honestly, I don't think this one is too difficult of a concept, so I'm not going to spend time reviewing it again. Looks like we do have a question or comment, though. Okay, so we have two questions. Is it just motor behavior, or is it focus too? As far as I know, so you're referring to the basal ganglia. That's a good question, actually. So you're asking, so these are generally considered motor diseases, but they do, I suppose, have a cognitive component as well. And so it's an interesting question, which I actually don't know the answer to, but in fact, I've never even thought about it. Cognitively, or as far as attention is concerned, do these individuals kind of have analogous things that happen to their mind that also happens to your body? I'm assuming that's the kind of motivation for the question that I just received. And so for Huntington, I don't know the answer, but for Huntington's, you would make the prediction that their attentional state would kind of be changing from one thing to the other, to the other, to the other as well. And for Parkinson's, you would imagine that their attentional state, their mind would tend to fixate on things. If there is kind of assuming that there is kind of an analogous attentional issue as well. I don't know. There's definitely cognitive mental issues that correspond to these two diseases. I don't know how similar they are to the motor disturbances. So I don't know if the nature of the cognitive impairments with Huntington's disease are similar to the nature of the motor impairments. And if the nature of the cognitive in Parkinson's disease, those impairments are kind of analogous to the motor impairments in cognitive in Parkinson's. That's a super interesting question. I've never even thought about it before. So I don't have a better answer, but I definitely understand why you're asking that question. Let me look at these others. Yeah, so that question I was just answering, is it just motor behavior or is it focus too? Which by focus, I think you mean like attention or cognitive thing. So good question there. The other question, how do Huntington's disease and ADHD differ? Which is kind of similar to the question I just answered. So ADHD, it doesn't have the motor impairment. That's like the really clear difference for ADHD and Huntington's disease. I understand the reason why you're probably asking about this question, because Huntington's disease is characterized by too strong of an excitatory signal, which causes changes of one motor behavior to the other, to the other, to the other. In ADHD, there probably is kind of a similar thing which occurs, but for the attentional system only. For ADHD, the people with motor or with ADHD, attention deficit hyperactivity disorder, are not constantly moving. At least they're not moving in the same way that individuals with Huntington's disease do. In fact, yeah, if you watch this video, in fact, maybe if it's quick, I'll do it right now. Yeah, why not?
Washington across the Delaware. So I'm sorry that you're upset. I died with people I should have died with. Yeah, it was sad. There's a few times in tears in the face. It's weird to the last. I'm going to call people, but this letter they're going to get from me explaining why it had happened. Did you think they wouldn't understand? No, they don't.
So that's an individual with Huntington's disease, and you can see that person has those uncontrollable movements. An individual with ADHD, their mind might be kind of like that, but you don't see it outwardly represented by the body moving constantly. But it's kind of an interesting thought to think that maybe the minds of people with ADHD, the inside of the person that with ADHD might kind of be acting like the outward motor behavior of this individual right there. That answers those two questions. Those are good questions, deep questions you guys are just asking about how these motor conditions, whether they have cognitive impairments, which kind of are similar or analogous to those motor behaviors. Good question, and I don't actually know the answer for sure. But yeah, thanks for asking. Moving on. So the disease we just watched was hyperkinesia, Huntington's disease. And there's that Parkinson's one you should consider watching as well. Don't forget to understand set shifting and which of those two diseases it corresponds to. And then we'll move on now. I'm trying to see where we left off. Yes, we left off talking about motor cortex. So the brain regions that we're going to talk about, or we've already talked about the basal ganglia, which I just said was selection is the way I've phrased it. It's involved with the selection of motor behaviors or actions, or the initiation, kind of a similar word, selection or initiation of motor behaviors. And the basal ganglia is related to those two diseases we were just talking about. We'll also talk about the cerebellum, which is certainly a subcortical region in the back of the brain. And then the brain region we were talking about last time, primary motor cortex, that's in the frontal lobe, premotor cortex, frontal lobe, supplementary motor area, 3 frontal structures. And then the brainstem, we're really not going to talk too much about in detail. The brainstem is just kind of thought of to be output to the body, which can move the effectors. Some signals to move are made centrally, and then those signals are sent down to the brainstem, and then eventually they reach the muscles, the effectors themselves, which will move because of the output sent via the brainstem. So yeah, last time we left off talking about primary motor cortex. And so those 3 frontal areas, MC is motor cortex, SMA, which we'll talk about more today, supplementary motor area, and then PM is the premotor cortex. These are all the frontal lobe motor regions. Right here is the central sulcus, which we've talked about now kind of a lot in this class. Whoops. Motor cortex is on the anterior side, the frontal side of the central sulcus. On the posterior side is somatosensory cortex or touch cortex, kind of primary sensory area for the sense of touch is right in the posterior side. That is on the parietal lobe side. So the frontal lobe structures, we're going to finish today talking about all these, including resuming where we left off with the primary motor cortex, MC. The basal ganglia we already talked about last time. Here's the cerebellum. We're not really going to talk too much about the brainstem. We just mentioned the brainstem is kind of the output to the body. It causes the movements of the muscles themselves. So yeah, we'll continue on with the motor cortex, which is what, yeah. So we should review this stuff a little bit, just a little. The difference between preferred direction and a population vector. These are like the main two concepts really about motor cortex. I guess, okay, another concept, which we've mentioned before, that the motor cortex, primary motor cortex, it's typically thought of as being the part of the brain which controls voluntary movements of the contralateral side of the body. So the right motor cortex is thought to control movements of the body that are voluntary on the left side of the body. So there's the contralateral organization of motor cortex. And it's typically thought, I'll reiterate here, voluntary behaviors. Motor cortex, primary motor cortex is important for voluntary behaviors. So that's probably the main definition of primary motor cortex. But those two additional concepts that we talked about last time, preferred direction is shown here. So all of these are a single animal making these movements. It's either making movements from the center out, or it's making movements from the out towards the center. And these dots, each one of these dots is actually coming from the same neuron. So it's not like they're measuring from a whole bunch of different neurons. They're measuring from like one neuron. All of these are taken from that one neuron. And they're trying to find in this study the direction of motion for which this given neuron fires the most action potentials. And if I'm remembering correctly, the answer would be, let's see, 270. Yeah, 270. So right there, there's a lot. Right there, there's a lot. These are the preferred direction of this neuron is 270 degrees, because those are the directions of movement, 270 or 270, where the most amount of action potentials are being fired. So once again, preferred direction is the direction of movement of a given body part, which causes a neuron to fire the most action potential. So there's many neurons in motor cortex, primary motor cortex. Different neurons have different preferred directions. So depending on the specific movement you are making, different neurons will become activated. So that's preferred direction. The more complicated concept is population vector. So that's shown, and this is where we left off, I believe. These things right here, each of these has a population vector in it. The population vector are these long dotted lines with the black dotted lines with the arrow at the end. And I kind of mentioned last time that when you're making a movement, the population vector is kind of how like all of the information in the motor cortex is kind of combined or integrated to form this population vector. And I think probably the most helpful, like any one of these little things right here is helpful for understanding preferred direction and its relationship to population vector. Looking at one of them, let's just go to this one right here. Each of these little orangey brown things, which is sticking out of here, these represent different neurons in motor cortex. So there's like 20 or 30 neurons in motor cortex right here. And the direction that each one of these orange things is pointing is that neuron's preferred direction. The length of each of these orangey brown things is the amount of action potentials that neuron fires. And so when the movement that you are performing is 90 degrees, the way that movement is represented in the brain would be something like adding up or summing or averaging the activity of all of these different neurons. Each of these neurons has a different preferred direction, but those neurons whose preferred direction are close to the intended direction of movement, the population vector, those are the neurons which fire the most action potential. It's like you notice over here, the neurons which are pointing down, very little activity or almost no activity there, which makes sense because the direction of motion is this way. So all the neurons whose preferred direction are pointing the other way, they shouldn't be firing at all. It's those neurons whose preferred direction are in the basic direction of motion of the intended direction. Those are the neurons which fire the most action potential. So each one of these neurons has its own different preferred direction. The population vector is kind of like the sum or the average. You can kind of think of it either way, sum or the average of all of these individual neurons. They sum together to give like a single direction. That's the direction that your body actually moves. So this is a helpful concept, population vector. It's been used now because there are computers which can kind of measure brain activity. And I don't talk about it too much in the lecture, but it's a helpful thing for individuals which have problems like with paralysis, where now using computers, the computer can kind of read out the brain activity of a given individual, and it can infer the direction that the individual wants to be moving by measuring the neuronal activity that is being from areas like primary motor cortex. And a computer can basically learn, oh, whenever I have kind of this pattern of neuronal firing, then this means that I want to be moving in a 90-degree direction. So these population vector ideas can be used by a computer that can help a person who's paralyzed to control a prosthetic limb, a prosthetic device, using their brain, basically. If their body isn't working for whatever, the connection between their brain and their body isn't working, you can use measurements of that individual's brain by itself. And then those measurements can be used to control a new limb, a prosthetic limb, using this idea of population vector. The brain uses these ideas, measures neuronal activity, and then outputs a movement using this idea of population vector. Okay, so I think this is new stuff. This is probably not as difficult as what I just showed you. It's kind of, but it's this finding right here is supporting the idea that primary motor cortex isn't just involved in the execution of motor behaviors. In fact, let me go back to something real quick. Yeah, so primary motor movement planning is another thing. So I already talked about how it's important for control of contralateral side of the body, especially voluntary movement. But planning movements is another thing that primary motor cortex does, and that's what this slide is all about. So this is a study, it kind of reminds me of the attention studies that we talked about in chapter 7. It's similar to those because there's like a cue, which is what these things are. And this cue is telling you basically, in a certain amount of time into the future, you're going to be moving your body in some direction, and that direction will be the direction of the cue. So here, this cue is telling you in 500 milliseconds, you're going to move this direction, and 500 milliseconds, you'll move this direction, and 500 milliseconds, you'll move this direction. These are cues that tell you 500 milliseconds or so into the future, here's the way we want your body to move, and you'll receive a go signal at that 500 millisecond time into the future. So this like part between this cue signal and the go signal, which is telling you to move, that's like the delay period or the preparatory interval, which we had a similar concept in chapter 7 on attention. And basically all of this is showing is that the motor cortex plans actions before it's actually performing them. So if you are thinking about doing this movement right here, and then you measure motor cortex, primary motor cortex, frontal lobe structure, right anterior to the central sulcus. If you're measuring a brain activity before the actual movement, you can see that the brain activity, those neurons which represent that are closest in preferred direction that is, which cause the population vector to be in the same direction as the movement you're intending, those neurons are actually firing before you perform the actual movement. The movement is performed at the go signal. Even before that go signal is received, your motor cortex is preparing to perform the movement that it's going to perform. So this is planning. Motor cortex is important for the actual execution of a motor behavior, but it's also important for even before that motor behavior is performed. It's kind of representing the motor behavior before it happens. So planning of movements as well. So that was motor cortex. That was a frontal lobe structure. And then now we're going to talk about cerebellum, and then we'll go back to talk about those two remaining frontal lobe structures before I think we'll call it a day for the motor chapter, the action chapter. So cerebellum, we have a lot to talk about regarding the cerebellum. Actually, it's probably definitely one of the brain regions whose kind of sole purpose is thought to have to do with motion or action, the cerebellum. Out of all the brain regions we've talked about, it's a very big one, has lots of neurons, and its sole purpose or its main purpose appears to be related to the motor system. And there's kind of three different motor purposes or kind of motor concepts which the cerebellum is thought to be relevant to. One is retrieval or consolidation of a long-term acquired procedural memory, that is a non-declarative memory. So like a memory of an action that you have acquired. So I think the best examples of this would be things like sports moves that you have learned through practice, repetition. I always think of hitting a golf ball, serving a tennis ball, maybe pitching in baseball, or hitting anything where you kind of do this, have practiced a movement in a sport over and over and over and over and over again, trying to get the movement perfect and as efficient as possible. The cerebellum is probably one of the main brain structures that is involved with the memory of what your body is supposed to do while performing that given action. Looks like we have a question or comment here. Yeah, and the question is, doesn't the cerebellum help with balance? Yeah, so I consider that part of the motor system. The cerebellum definitely helps with balance. Individuals that have cerebellum lesions or don't have a cerebellum at all, which does occasionally happen, presumably, will certainly have problems with balance. So I didn't mention that one here, balance, but it's definitely kind of part of this, the theme. Cerebellum is important for motor activity in general, but balance is an aspect of motor activity. So yeah, that's definitely true. So I'm going to provide some evidence that the cerebellum is important for retrieval of long-term motor memories. The cerebellum is also important for classical conditioning. And then finally, this idea of a forward model, which right before class, I kind of added some terms here. When I'm talking about forward model, I'm also talking about sensory motor learning, or adaptation is the example I'll give. So there's kind of 3 different words or 4 different words that describe this: the forward model, sensory motor learning, adaptation. Those are all kind of related to the same function of the cerebellum: forward model, sensory motor learning, adaptation. And the example, I kind of like this example right here, but then I'll give some more scientific, study type of examples here in a second. So an example of this forward model purpose of the cerebellum, this is an interesting one. The cerebellum is thought to perform in this function predictions about what it's going to feel like when you perform some type of an action. So it's forward looking in the sense that you are just about to perform some action, some motor behavior, a motor sequence of behaviors. And the cerebellum, it's thought to be like, okay, when I perform this action, when I perform this motor behavior in a second, what is it going to feel like? And when I say feel like, that's what I mean by sensory consequences. That's the feel part. Predictions about what it's going to feel like for an action that's kind of currently occurring, or one that's going to occur in the near future. You're moving your motor system, and your cerebellum is thought to be making predictions. What is it going to feel like? You mostly with the sense of touch, presumably, but maybe also with the sense of vision as well. What's it going to feel or look like? What's it going to censor? As far as my sensory systems are concerned, what are the inputs? What are things going to feel like to those different sensory systems while I'm performing the action. So an example, classic example here is like when you, when you're thinking you're stepping on the very bottom step. So you're going downstairs and then you do that last step and you think, now you think you're at the bottom and you think that the next step that you're going to take is flat ground. You think you've reached the bottom of the stairs, but you really haven't. And so then on the next step, it's actually lower, like you're expecting it to be flat, but there's actually one more step there and you'll kind of trip a little bit. And the reason you'll trip, or actually I had a friend who broke her foot when she did that on the stairs once. The reason it's kind of, messes with you when this happens is because you form an expectation, presumably with your cerebellum, for I have reached the bottom now. So when I take the next step, I'm going to feel on the bottom of my foot, the world pushing up right here again. I'm right here and then I'm at the bottom. So that next step, I'm going to feel the world pushing back up on my foot right here. That's a prediction you're making, a forward model or a sensory motor prediction, which is violated. You turned out to be wrong when you have one more step to go. So you're expecting to feel something here, but the step is actually down here. So you're expecting when I get there, my foot will will have support from the floor, but you end up having to go further down. And so that's when you trip, or in the case of my friend who she broke her leg her foot stepping down from a stair when she didn't realize that there's one more stair. So that's cerebellum. I think we have questions or comments, so let me get to these before I forget. Yeah, okay, so why does everyone seem to have different balance abilities? Do some people have more developed cerebellums than other? Or it's just muscle memory and balance? I think it's kind of all of the above. So, I mean, it's hard. You can't just isolate a single reason why some people have are more athletic or have better physical abilities. There's many different parts of the brain that have to do with this. I mean, if you have really big like muscles and stuff, that will help. That's like a completely physical thing, but that will oftentimes help with things like balance and motor activities. Having so it's not all people that are good at motor behaviors and balance abilities. Is it just because of the cerebellum? The cerebellum is one important factor, but it is not the only. The physical muscular structure of the person themselves is important. And then there are also other motor regions which are involved as well. However, the cerebellum is probably one of the more important. And I would be very interested, for instance, to like look at the cerebellums of like professional athletes and then compare them to non-professional athletes. And yeah, I imagine you would find some really big differences in the cerebellum of people have really effective bodies compared to people that don't. That would be a prediction, but unfortunately, there's not, as far as I know, not tons of research on this. I don't think professional athletes, for instance, don't usually volunteer for the type of research for this type of research, for instance. So I don't know the exact answer, but yeah, I would imagine the cerebellum is an important difference between athletic and non-athletic people. Is the cerebellum similar to the prefrontal planning for negative and positive outcomes? Like if I touch fire, I will feel hot and hurt, so don't do it. I'm not for sure I understand the question. Is the cerebellum similar to the prefrontal planning for negative and positive outcomes? I don't think the cerebellum necessarily thinks about positive versus negative outcomes. I think of the cerebellum more as any type of behavior. Yeah, I think of the cerebellum as any type of behavior where you have any type of learning. It's like all of these different functions right here regarding the cerebellum have to do with learning. And I don't know if it's necessarily learning like the emotional valence of things, like this motor behavior is good, this motor behavior is bad. It's just more about committing that motor behavior to memory. That's how I think about it. And so let me go into these examples, and I think it'll clarify things a little bit. Here's the first one about the formation and consolidation of a motor, a procedural memory. So this is a study which shows, I'll kind of go to the punchline. It shows that the cerebellum is highly involved in the retrieval of a motor behavior when there's been practice, motor practice or learning of a given motor behavior. So that's what this is right here. So this study had two phases, like a learning phase and then a test phase, like a phase later on. Once something has been learned, you have a long-term memory of it. The thing which is learned is the motor behavior in this study. You can kind of think of it, the person was laying down in a fMRI scanner, so they can't move a lot, but they were moving, they were performing like what I call like a hand dance. They showed people a picture, and that picture that they showed them basically represented the directions of motions that the participant was supposed to move their hand. And they were supposed to basically memorize these motions involving their hand, moving their arm and their hand while they're holding this little thing. So it's like a hand dance. And they get practice with it. That's what this is right here. And when they're practicing, when they're learning the hand dance, there's activity in the parietal and frontal lobe. Then later on, once they've like acquired it, once they can now do the hand dance without having to like look at the visual thing about what they're supposed to do, once they basically have it committed to memory, a new set of brain regions becomes activated. So this is like once it's become kind of like, you can do the hand dance and you don't really have to think about it anymore. It's become kind of automatic or automated. There's still parietal lobe activations. The really key finding here, though, is that there's cerebellum here. So this is when you're performing an action that's been well learned. The cerebellum becomes involved with the retrieval of that action. When earlier you're performing the same action, when you're learning it before it's been well learned, there's no cerebellum activity, or at least significantly less. And there's significantly more cerebellum activity once that activity has been well learned. So this is consistent with what I said. Those activities like serving a tennis ball, hitting a golf ball, also things like musical instruments, playing a kind of song on a musical instrument. Those type of motor behaviors where you practice a motor routine several times until you get it. The learning or the getting it part of that motor behavior involves the cerebellum primarily. Other structures as well, but the cerebellum is important for the retrieval of the retrieval of a non-declarative, that is motor behavior. So that's part one. So I'll go back to these real quick. So the things about cerebellum, I just showed you that study about the hand dance. That supports this idea that the cerebellum is important for retrieval or consolidation of procedural, that is motor, non-declarative memories. Now I'll provide you some evidence that the cerebellum is important for classical conditioning. It comes from this study. This abstract is a little bit confusing, so I'm just gonna, I oftentimes include the abstracts just so you can see where I got the study from. But I'm just gonna kind of describe this one aspect of the study because it's most enlightening as far as understanding the role of the cerebellum in classical conditioning. So if you recall from introductory psychology, classical conditioning is the idea that you can elicit a response, usually a motor response from an organism if an unconditioned stimulus is paired with a conditioned stimulus, which is what's going on here in this study. So the way this is it's like the eye blink paradigm. Yeah, and it says right there, eye blink responses. And so the way this works, the unconditioned stimulus is usually a puff of air, which is shot, a little puff of air, which is shot directly into an animal or a person's eye. It's harmless. It's just a puff of air. But the thing that it causes is a blinking response. That's a motor behavior, a blinking response that doesn't require any learning. When you shoot a puff of air into a person's eye, it's kind of a natural defensive response to blink your eye. So that's like the unconditioned stimulus is the puff of air. The unconditioned response would be blinking of the eye. In this study, what they want to see is, can they train animals? I believe they were rats in this study. I don't know for sure if it was rats actually, but it was some type of animal in this study. And they want to train these animals. Are the researchers able to train the animal that every time it sees, I believe it was a light that turns on. Does it say the conditioned stimulus? So I don't remember exactly what the conditioned stimulus was, and I don't think it says here, but just imagine it's a light, or maybe it's a sound. It's some type of neutral stimulus, which normally would not cause a person or animal's eye to blink. So just think about a light turning on. or a piano key being struck, something like that. That's the conditioned stimulus. The researchers want to know is can we pair the puff of air with the conditioned stimulus, like the piano key or turning on of a light, so that eventually when we just play the piano key by itself, but don't blow a puff of air into the animal's eye, can we cause the animal to blink? The animal learns the association between hearing a piano tone or seeing a light turn on with receiving that puff of air and then having to blink its eye. Can you train animals to form this association between the piano key, the conditioned stimulus, and the puff of air, which caused the animal to blink? And the answer is yes. And the cerebellum appears important for that. So in this study, the part of the left cerebellum was lesioned. And so here, this is the CR. The dependent variable here is muscle movements of the muscles around the eye. So here is the animal's amount of blinking responses of the left eye. So there's some important details here of the left eye after that cerebellum has been lesioned. And so here you're hitting a piano key or you turn on a light and you've been training the animal. You've been trying to train the animal when it sees or hears that conditioned stimulus, you're trying to get the animal to blink. But the animal doesn't do it here. So they tried for like 3, 6, 9, 12 days or something like that to train this animal whose left cerebellum was lesioned, training this animal to blink and respond to the conditioned stimulus. A piano key, which had been paired with the puff of air blown into the eye. Eventually, can we make it so that we press the piano key, the animal will blink? And you can see there's no muscle movement. It's a flat line right here. The left eye, they were not able to train the left eye to blink by pairing it with a piano key. That is a conditioned stimulus. However, right here, this is when they started trying to train the right eye. So instead of, they would blow a puff of air into the right eye and they would simultaneously push a piano key during training. And then eventually they would push a piano key by itself. And you would notice that in this right eye, there was learning. The evidence of learning is the fact that you start seeing increases in muscle activity right here. This is in response to the conditioned response, like the piano key or some light turning on, which causes learning in the right eye. And then you go back. This is when they go back to the left eye again. They're like, well, if we can teach them the right eye, let's try the left eye again. And they still can't get it. The left eye in this study would just not learn. The right eye would learn. This is the right eye right here. But the left eye just would not learn. And this is interesting because once again, it was the left cerebellum was lesioned. When the left cerebellum was lesioned, they were unable to train the animal to form conditioned responses on the left side of the body. So one thing that is interesting about this is the cerebellum is kind of an exception to the rule. Most parts of the brain have this contralateral organization where the one part of the brain controls the opposite side of the body. The cerebellum appears to be an exception of this. And there's more than just this one study that supports this idea. The cerebellum, those parts of the brain appear to control ipsilateral sides of the body. When the left cerebellum was lesioned, the researchers were unable to train conditioned responses on the left eye. But when they switched to the right eye, they showed evidence of conditioned responses. And then when they switched back to the left eye, still nothing. So the left eye wasn't able to learn, but the right eye was after a left cerebellum lesion. Supports the idea that the cerebellum is important for conditioned responses for the ipsilateral side of the body. So one more thing. So we just talked about, that was conditioning. So we've now talked about the cerebellum is important for retrieval of that hand dance study. The conditioning, eye blink conditioning we just talked about. And then finally, this last one, the forward model idea, which I'll remind you, this is some synonymous terms, sensory motor learning or adaptation. This has to do with, once again, the cerebellum is important for forming predictions about the sensory consequences of a movement. So in this example, when you think a step on the last step, but there's really one more. The sensory consequences are most relevant here would be the sense of touch, what I'm expecting to feel on the bottom of my foot, depending on whether there's a 0 stairs or 1 stair left to go. The example which is talked about most in the book is a type of, it's still the same concept, but it has to do of, a forward model, but it's a visual sensory type of thing instead of that tactile sensory thing. So let me explain it, it will make more sense. Here's a study where basically people are aiming like a ball or some type of an object at a target. So it's like target practice, basically. And they start and people are accurate, pretty accurate. They're usually right. So 0, this is where this is where the thing you're throwing goes. And the target is at 0. So you can see here, this is like the control condition kind of. The people are hitting the target somewhat accurately. But then people put on these things in the study called prisms glasses. So I've never worn prisms glasses, but I think you can kind of imagine they distort things visually. And so like you can think of the prisms glasses where everything is like shifted either to the left or everything is shifted relative to the right. So the world when you're wearing the prisms glasses does not look, it's not accurate in the same way that it was when you were not wearing prisms glasses. So before right here, this is like your normal situation. When you put on the prisms glasses, the world is now visually distorted. And they want to see in this study, are you able to still hit the target? And if you look, right when people put on the prisms glasses, they're way off target. So the visual distortions, which make the world seem shifted one way or the other, is influencing the accuracy of their aiming, as evidenced by the fact that they're, negative 50 right here. They're way off target right here. But as you can see, that they eventually get used to the prisms glasses. They adjust to the prisms glasses, which is evidenced by the fact that towards the end of this trial, they're right around the target again. So what this means is that these people's cerebellum is working. They're adapting. They are learning. And what they are learning is, they throw the ball and then they see that for these trials right here, I threw the ball straight and I ended up missing the target by 50 units to the left. So what I need to do now is aim a little bit more to the right to kind of compensate, to adapt, so that eventually I can hit the target again. So once again, they're 50 units off to the left. They throw the ball, they think they're throwing the ball straight, but it ends up going, because of their distorted visual from the prisms glasses, they're off by 50 units to the left. So they have to compensate. And visually, they have to say, okay, I appear to be off 50 to the left, so I need to compensate by going 50 to the right. And so then they'll aim the other direction, and then eventually they're able to get back on target. So this shows that their cerebellum is working. They are able to adjust the forward model. They're able to learn with new visual information, even if it's distorted. They're able to kind of change their motor approach given the feedback they're getting from the visual system, even though the visual system, that their information is distorted or inaccurate, they're able to adjust. Then if you take, what's interesting is that if you take off the glasses, the prisms glasses again, they actually, and then you look what they do when they're, in their normal state, again, not wearing them, they actually at first overcompensate too much to the right. And you can see that right here. They've overcompensated too much to the right when they're not wearing the glasses after wearing for a while, but then eventually they get back to hitting the target. So this is example of that forward model, the using predictions about sensory consequences of some motor behavior, and the ability to kind of update your cerebellum can update what it's expecting to, in this case, see. However, in this person right here, this was a case study. So this is a small sample size. So this is an individual though with a person with a cerebellum lesion and performing the same aiming task. At first, at the beginning of the experiment, they're accurate. So this doesn't mean people with cerebellum lesions, this doesn't mean they're completely inaccurate. They can actually hit the target okay. At least this person could. But then they put on the prisms glasses. So remember, the prisms glasses distort the world, so it shifts everything to the left or right. And for normal controls, that required adapting. That required kind of updating the forward model to compensate for the distortions of the prisms glasses. But the individual with cerebellum lesion wasn't able to do that. And you can see this because they are staying around -50. They're 50 to the left of the target consistently. Unlike the other people, they're not going back up to the 0 and hanging out right there. These people are consistently inaccurate once they put on the prisms glasses. So it appears that their cerebellum is not able to adapt. It's not able to update its predictions based on the visual information that it's receiving. That's really the key finding. And then they take off the prisms glasses, and there is some compensation, and the person doesn't really ever get back to hitting the target. So this is an example of sensory motor learning adaptation. Although it's a small sample size, I believe this is literally a single participant. The participant that had the cerebellum lesion wasn't able to adapt, wasn't able to update that forward model like the controls who had intact cerebellums. Okay, so we have 2 more brain regions. Neither of these are we going to talk about a ton. I have like one study for each of these. And these are both frontal lobe regions. So these are the last 2 motor regions. Let's go back to our little picture. Oh yeah, we got one right here. So regions that we've already kind of finished talking about. Primary motor cortex, we talked about that. We finished talking about that today. The basal ganglia, we talked about last time. We finished talking about that today as well. The cerebellum, we just got talking about. There's kind of 3 different things we talked about. The cerebellum, the brainstem, we're not really going to talk much about. The last 2 are these 2 frontal lobe structures: supplementary motor area, SMA, or PM, which stands for premotor cortex. These are the 2 frontal lobe structures, the last 2 that we'll talk about. So the supplementary motor area, the SMA, is thought to be involved with voluntary actions. But it's particularly important for like before the motor action has taken place. And that's why it's called this thing right here called the readiness potential. The readiness potential is measured with EEG. So electrodes are placed on the scalp, but the signal for the readiness potential is strongest right in the central parts on the frontal electrode. So right here, this is where the readiness potential is strongest. And so this readiness potential is right above those central midline electrodes in the frontal lobe, which suggests that it might be coming from the supplementary motor area, because the supplementary motor area is right underneath there. And there's some other evidence as well that the supplementary motor area is the source of this so-called readiness potential. What this is basically an electrical response measured with EEG on the scalp, which builds from the time once a person is right before they're about to make an action to the time that they make an action. So here is the best graph for this right here. So this is the electrical signal, which is measured from SMA, the central electrodes in the frontal lobe right here. Time point 0 is when the person actually makes a movement. And it's a voluntary movement. Literally, the way they do these studies is they tell the participant, when you feel like wiggling your finger, wiggle your finger. That's it. And then at different points in the study, the person will wiggle their finger. And that's what time point 0 is right here. Time point 0 is movement onset, when they actually move their finger. But what they're interested in is what happens right before that. And they find that about 1 second before this voluntary action, there's this increasing negativity. That is the readiness potential. So it's kind of like before you actually do this voluntary movement, your SMA is kind of preparing to perform it. In other words, this is the brain is starting to prepare for this movement about 1 second, at least 1 second before you actually produce it. And that's the SMA. So it's a voluntary action, just moving your finger. It's measured from those central electrodes. The SMA is basically the response of your brain for about a second before a voluntary movement. It's kind of a preparatory thing. It's as though your brain is preparing to perform that voluntary movement, and it takes around a second to do it. And it's characterized by a building negativity. I want to show you that. Yeah, if you look, negative is up, positive is down. The negative numbers right here is before the action is performed. Starting around negative 1 second before the action is concerned, things are starting to go up in the negative direction until the action is performed, when things go back down to the baseline level. So this is the readiness potential, the building negativity in those moments about a second before a voluntary action is performed. And then, so that's really all I have to say about supplementary motor area. The most famous thing about it is its connection to the readiness potential. And then the other frontal lobe structure is the premotor cortex. It's different. These are kind of, both of these are involved with kind of preparation, but they're different in the sense that supplementary motor area is involved with preparation of voluntary actions, whereas premotor cortex is important for the planning of externally guided actions, externally guided motor behaviors. And as I said, is guided by spatial position. So there's a study shown here, a neat one, regarding premotor cortex. And they're measuring, so this would have to be like studies like an animal, probably a monkey, because it's kind of a sophisticated task. And there's different spatial cues that the monkey is given. And that's what these are right here. And the animal is given like 2 of these at the same time. And basically what this is showing, when the animal sees this, the animal knows, okay, I'm going to be responding to a target, and that target is going to occur at one of these 2 spatial positions. And they're measuring neurons in premotor cortex, this frontal lobe structure. This neuron right here is a premotor cortex neuron, which responds most strongly when in response to stimuli which was presented in this spatial location. And then this neuron right here is responding to stimuli when they're in this spatial location right here. And so they're presenting both of these at the same time, and so it's ambiguous. And the animal's like, okay, am I going to be moving in this direction towards that in the upper right, or am I going to move down into the lower left? And the animal doesn't know yet. It's ambiguous because it's been told you're going to be moving to one of these 2 objects, either upper right or lower left. But then there's a waiting period, a delay interval, a preparatory interval, and they're measuring the brain response during that time. What happens after that delay interval, after that preparatory interval, is that then there's another cue which is given. This disambiguates. This tells, okay, you are going to be moving in the direction of the red circle. So basically, that says once the animal sees this, they know, okay, I'm not going to be moving to the blue one, lower left. I'm going to be moving to the upper right. I think they literally have the animals make a saccade, so an eye movement to the direction of one of these 2. When the animal sees the red cue, that says, okay, move your eyes to the upper right. And so the crucial thing is what happens during that preparatory interval, that delay interval right here, where the animal doesn't know which of these 2 locations it's supposed to move its eyes to eventually. It's going to move its eyes to one of these red or blue locations, upper right or lower left. And during the delay interval, you can see that in the premotor cortex, both of those potential actions are represented at a very faint level. So it's like the premotor cortex, it's externally guided in the sense that you have these locations out there in the world that you have to act with. In this case, you're moving your eyes to one of those 2 locations. And before you know with certainty which of those 2 locations to be moving to, the brain represents both of those possibilities. And that's what this is. If you look, there's that kind of yellowish green, which represents, that means there's activity here in this neuron. This is the neuron that responds to movements in the direction of the upper right. This is the neuron that responds to movements or causes movements in the direction of the lower left. During this delay interval, when you're not moving at all, both of those 2 possible movement directions are being represented. So it's as though the premotor cortex, it's representing all of the possible movement options that you have. So this is what's neat though, is, you know, it's representing like the possible things you could do, not the thing necessarily that you actually do. The thing you actually do would certainly be represented in primary motor cortex. The premotor cortex though represents the possible choices that you might make. Upper right, red, or lower left, blue. You can see that because there's positive, you know, the yellow, green, red activation here during the delay interval. Then once that color cue comes, which makes everything certain, the animal knows exactly, oh, okay, I'll be moving to the upper right. Then you can see that all of that activation in the other premotor cortex neuron, which was representing the possible movement to the lower left, goes away. So really, I'll go back to the externally guided actions, which are important for interacting with objects that appear in different points in space. And I guess I didn't say this, but the premotor cortex, an important thing about it is that it represents potential actions that you can perform. All of the different possible things that you can do, the premotor cortex appears to represent them before you make a choice and single out the one action that you're actually going to perform. So that's it for the action chapter. So I do have these 3 questions. We'll make these do, see, today is Monday. I don't see any reason why I have to be super hurry about this. So we'll make this one due Friday at 11:59 p.m. That's what we'll do, Friday at 11:59 p.m. And it's just these 3 questions. The 2 videos on slide 10, let me make sure that that's still slide 10 actually. The 2 videos that I'm referring to, yeah, it is still slide 10, are these 2 videos right here. So I want you to watch both of these videos and then talk about, one of them is Huntington's with hyperkinesia. The other one is Parkinson's with hypokinesia. And I want you to kind of describe the movement behaviors that people are performing and why one makes sense to consider it a hyperkinesia and why the other one makes sense to call it hypokinesia. And then the other question, what is preferred direction? What is population vector? These are these terms. They're kind of difficult, having to do with primary motor cortex. I want to make sure that you know the difference between these 2 terms, preferred direction, population vector. And then the eye blink conditioning study right here. I explained it to you earlier, but I just want to make sure that you understand what I explained. And so I want you to try and explain how the findings of that study back to me. So I'll make sure it's still on slide 24. Yes, it is. That is on slide 24. So yeah, if anyone has questions or comments, feel free to stick around. Otherwise, I will see you Wednesday.
Thank you.
Thank you. Take care.